I copied over the examples that are remaining from the last episode, and we're going to finish them up. We had left off on this one, I think. So we need to prove that or inside of an exist statement commutes basically the associativity of or here. Do a structure, both cases. In the first case, we're going to assume there exists x such that p of x or q of x. So we'll say, call this the our intro x and the or, a bit more specific here, keep or q. And now it should be pretty clear what the strategy is. Recall from working with ors in the hypothesis that we want to use cases or match. In this case, I'm going to use match because that way I don't need to repeat myself with exact. So I'm just going to leave tactic mode because I'm ready to solve the goal completely. So we're going to match P or Q. In other words, this match is going to be one expression that solves the goal. And it's going to have a left side of HP, right side of HQ. Not sure why this goal is so convoluted. Okay, so I just needed to put a sorry there. So now we need to do orn.injection. We're going to need to do the right side, I think. Oh, well, I'll just guess. And then we need to build up our exist statement. We're going to do that with the angle brackets. So we're going to say, basically, if we have to prove an or, it suffices to show the left side by or.injection left. And of course, on this one, we're going to do the same thing, but for Q, and we're done. In this one, we need to introduce two separate exist statements. X, call this one Y. Actually, I'm going to call this X2. So I'm going to do a backslash and then 1 to get the sub2 notation. This is going to be HQ. And I'm getting an error. Did I not introduce the right stuff here? Exists X such that P of X, or there exists X such that Q of X. Oh, I'm trying to assume this on an or. Silly. Okay, we're going to have actually the same exact structure here. And these will be the arguments. So we're going to do, actually, this is a good example of our cases. So our intro would work for this if we had these two, this exist statement and this exist statement as a hypothesis, sorry, as an and in the hypothesis. Since they're an or, we would have to match on, we would have to say something like assume this whole thing and then match on that, but we can do that in one step with our cases. So instead of doing, I mean, we could have done that up here too. I guess I just thought of it now. Our cases. And our cases uses the bar, vertical bar, to do a pattern match on or, and it will split the goal into two cases. We actually don't need the specified X because the cases are separate. And what's going on here? It's actually our intro still because we haven't introduced the. So now we have in both, in either case, right, we have X, but in the first case we have HP and in the second case we have HQ. So it's going to look very similar to the one on top. And I'm just going to guess that this is right. We're going to have the or.injection inside the exist statement this time. And be using exact here. And in the second one, Q to close the goal, right? Because we had to put we have to create the or inside the exist statement for the second one because we're proving, we started with it in outside, and then we have to prove it on the inside. Okay, but both of these have the same structure, and it should make sense to you why, because we're starting with ors and we're ending with ors, so we'll always be pattern matching. Okay, next one. We need to prove that there exists X such that P of X, if and only if it's not the case that for all X, P of X does not hold. This is a bit of a mouthful, so let's see what that means. Tabs got messed up again. I don't know why this keeps happening. Constructor. Oops. Sorry. And now we need to introduce the exist statement. Let's call this HP of X. Well, P is a proposition, P of X is good enough. Okay, so we have that. We need to show that there's not for all X, this is true. So immediately I notice that we have a not in the goal, which makes me want to use a proof by contradiction. And even better is that after I use a proof by contradiction, I notice that we'll have a for all statement in the goal, which is the same as having an implication in the goal. So we'll be able to introduce another x and show a contradiction. I'm going to say apply. Let's call that by contradiction. And we're going to intro for all. I'm going to call it a. And we're going to simplify the not at the intro. Oh, I think I messed up here. We should have, let's see, how it would have been better to do before we introduce the variable, because I really want to introduce x, right? So it's actually, it doesn't matter how we do this, but if I wanted to do the thing that I originally set out to do, then we need to simplify this first. So we need to say, rewrite not. This is a classical lemma, so say classical. And after I do that, we get rid of that. Two not-nots cancel, and we have for all x. Now, I thought that I would be able to introduce x here, but it actually doesn't make any sense because the for all is inside the hypothesis. Yeah, the way I was doing it was fine. In other words, these parentheses, right, make it so that I can't say intro x because the x is inside this. This is like a nested function. It's a hypothesis. You wouldn't be able to do it with a nested function either. So say intro fa up here, rewrite classical not. Oh, say it after just to make our lives easier. And then we are going to specialize. And I think I forgot to explain this last video, but specialized, it applies a value to a function when that function is not in the goal. That way it's the equivalent of saying apply for the goal. It's similar. Maybe it's not equivalent. Not quite sure. Okay, so basically what we need to do here though is we have to say that, well, if for all x not p of x, then if we have an x, then we should be able to simplify this to not p of x. Function application, right? So we'll say specialize fa with x. And now you see that fa turns into not p of x, which is of course a function from p of x to false, and we have a p of x. So should be pretty clear. Okay, next one. So recall that this is just function application. So the book is, while I don't like the way the book does these sometimes with the whole like function, basically never using intro instead of, and instead using lambdas. The book does do this show false from this weird, when you're applying a not to something of its type without the not, basically to its opposite. It is more readable to say show false from that. So let's go ahead and do that just to be a bit nicer here. We can say show false from, and I think we need to say exact two. Next one, not for all x, not p of x implies there exists x such that p of x. So we'll say intro. We could do a proof by contradiction first, but I'm just going to say intro, not fa. And now we need to show that there exists x such that p of x. Well, let's do a proof by contradiction first. So we need to simplify with not imp. This is a lemma that relates not implication to an and statement. After we do that, we get an and in the goal, which we can assume, which would also have a not exists and not. Yeah, I get the feeling right now that I'm doing this the wrong way because I think probably an easier way to do this. So if we had said intro first, then we would just have to show there exists x such p of x. So maybe let's think of it this way. After we do this, right, we can have something, let's just make this easier on ourselves. So we'll say that this is not, we're going to rewrite NFA as a function. This is not x of type A, sorry, x of type alpha. Not x of type alpha, nested parentheses here, implies not p of x. And we have this by, I think I can just say literally NFA. Yeah, that's, you don't even have to use any lemmas to show that these are the same thing. So, oh, but it doesn't even have it in the, whatever. That's mostly for us anyways to reason about this easier. So it's okay that Lean's not changing it from a for all. I don't mind. It's a little weird, but okay. So that means that we have a function from x to not p of x. Go ahead and rewrite the not implication NFA this time. See what happens. So did not find an instance of the target expression. One of the things we can do here is we can say by exact and find maybe that would help. Oh, that doesn't help either. It's a little annoying. So not imp is from a not implication to, oh, I see. So we're trying to rewrite, that should still work. Let's try the modus ponens version. I mean, telling me I have it, but then when I try to apply the lemma, it doesn't think of it as the same type. Okay, maybe simp will work. I don't want to use simp here. Okay. That's not my intention. We're going to use only so that just skip the proof. Maybe we can specialize it with X. I'd specialize it with this whole thing. Get rid of the not. Yeah, this is weird. So we have a lemma. Lemma says not A implies B can be rewritten as A and not B. Is there one for all? I don't see anything for all. I mean, we should be able to show this on our own, but still, like, okay, let's prove it on our own. So, let's recall what this is. So A and not B. So that means we're going to have X and not B. That means we're going to have X and not P of X. So that would just be P of X. Okay, now what's the problem? What do you mean? Unknown identifier X? That works here? Okay. So a not is something that takes the inner part as an argument, returns false. So let's try to prove this first. Do we have something of this type? It's just a lambda. I could say by intro and whatever, but I'm not going to do that. Lambda x goes to not p of x. I mean, I don't have a not p of x here, obviously. I don't know how to do this. Let's see here. Maybe I need to do a contradiction and then rewrite the not exists as a for all. I think that's probably what I'll have to do. So let's apply by contradiction. Let's assume it does not exist. And then let's show that, how do we show this contradiction? Well, we have to show that not exists is the same as for all, which we actually, so we're basically using the same thing as this example. Yeah, so we just need to show this example now. So I'm just going to go to this example because why not? It's the exact same thing we're proving. So constructor not exists. And then we have to also assume X. We need to show not P of X. Well, we can do that by showing that this not exists. We can construct that. We'll give that as proof to not exist. So X and P of X. Okay, maybe we don't just have P. Ooh, interesting. Okay, that means we'd have insufficient things to show our goal, then we need to use proof by contradiction. Now we finally get to assume our P of X. Should not have gotten rid of the solution there before doing this. Okay, so after doing a proof by contradiction, we were able to assume P of X because you get this, right? And then I actually don't need to be doing this, right? If you have a not in the goal, I always forget this. If you have a not in the goal, you don't need these two steps of doing contradiction, not. You can do it this way. It's just extra work, right? If you have a not in the goal, it's a function that you can assume its argument because it's implicitly a function from P of X to false. So you can just assume P of X directly and then finish, right? So kind of silly on my part. Let's get rid of these extra lines that we don't need. Okay. Yeah, so was that what we needed here? No. Okay, what we need is in the second one, where we assume the for all. And we have to show it does not exists. So we also get to assume the exists statement, right? So it's a proof by contradiction implied. And so, of course, we should pattern match, unwrap that exists statement, and now we should have everything. Specialize f of a to get not p of x, and then apply that to p of x. Let's do that in two steps, not one. Specialize f a with x. Set. Yeah, I know, I was that lazy just now. This is also a running theme for me in Lean. If I copy what I'm trying to do. Like if I'm stuck on something, I copy it to a lemma, just like a minimal example. It's always so much easier to prove the lemma, right? For some reason, even though it's the exact same idea. So definitely that's a super pro tip, life hack. Yeah, copy your, like if you're stuck on something, make an example. It really helps. But before you try that, like try to do a have statement or two, because that's almost the same thing, but not quite. So we left off here. Let's just go to the beginning of the proof. So we introduced all the way. We introduced the not for all. We have an exists. So I think we can do exists out of limb here. I just forgot how to do this. So there's this function which says suffices to show exists NFA. All right, so let's start by showing what we know we can show, which is for all x, not p of x. Because we have, there does not exist x such that p of x. So we must be able to show that for all x alpha, right, actually I can just do a. For all x of type alpha, we should be able to show not. We can do this by intro x. We have to show not p of x. We have to do by contradiction. What if we apply exists.elim? It does not exist. Oh, why is this so hard for me? How do we do it in the bottom? A specialize fa to x. So we have to specialize. We're able to assume not p of x. That's why it's hard. No, I still have making the same mistake again. I can assume p of x here. It's a not p of x, so it's a function from p of x to false. So silly. Okay, so exact closes the goal. Doesn't close the goal. What? Exact can close the goal here. Sorry, down here. But it doesn't know how to do it up here. It's literally the same goal. Oh no, maybe I tried it in the second case. I didn't try it in this case. Yeah, it doesn't know how to do that, but it does know how to do this one. Yeah. So now we've shown that. Let's get rid of these lines. We don't need them. And I bet exact will be able to show this too. So this is literally this in Lean is the last have statement you showed. We'll call it FA, so it has a name instead of just this. And yeah, now it's a bit more clear. And then of course we can do the whole show false from thing. Make this even more readable. Okay, finally. So yeah, once again we have if we have an exist in the goal, then I'm pretty sure you need to have a proof by contradiction. Usually you need a proof by contradiction. Because otherwise, how are you gonna get the x that you need? Maybe you could make a lambda, but then how are you gonna get the p of x or the not p of x? Okay, that's good enough for me. So constructor, in this one, we're gonna show that there exists x such that not p of x, assuming not for all x. I think we'll just blindly apply proof by contra because we have an exist in the goal. We're gonna assume not exists. And now do the same thing. We have not exists. Do we have, I mean, this looks like exactly the same thing that we did up here. What's the difference? Can I not just copy this? Ah, okay, we have p of x. We don't have p of x. It does not exist. Oh, it's clear how to do this. So we have a p of x in the goal. So after proof by contra, we get not p of x. And now we have everything we need to build a contradiction. So this was just the same idea, but instead of like up here where we had p of x directly, we had to build it. So now that we have FA, oh look, the proof I copied works now. That's funny. All right, on to the next. Introduce the exist statement. Now we have not for all x. Do we get to, I think we get to introduce x now. We only get to introduce the for all statement as a whole. No problem. Now we can definitely specialize the for all statement with x. And we just have to show false. It's just very trivial. And we're done. Now there's a for all x, p of x applies r. So now we're working with functions or implications. We introduce the for all. and the exist statement. For all exists, specialize for all with x, specialize the for all with p of x. Can I do that in one step? I can. Fancy. And then we just have assumption because I'm too lazy to write exact. Okay, next one. Exists for all. Oh, thought I had finished. Right. This is a function. And the for all is just x, p of x. So because the for all is not a it's not in parentheses, we get to assume the x, right? In other words, this is the theorem we're proving, not this implies this. The parentheses are grouped to the right as they usually are instead of to the left, which means we get to assume x and p of x actually. So because for all is basically x implies p of x, which implies r, so we get to assume these two as hypotheses. Okay, so now we just create the exist statement, give it to the exist implies, and then that should be the exact goal that we're trying to solve here. So that would look like exact in r exists x p of x. Super straightforward. All right, last one. By constructor start. Okay, so now we're assuming an exist statement. X. Oopsie. This is not. Oh, it is an exist. Okay. Wait, is it? I can't tell. Yeah, okay, that worked. So now we get to assume R. So we have to create an X and a P of X. Exact should be able to do this. Yep, just to be consistent here, I'm going to use these as constructors. All right, last one. We have to assume R implies exists. We have to assume there exists X such that R. Oops, what happened? Oh, I'm confused. What exactly did we get to assume here? Oh, the implications inside the exist statement. Okay, right. So we don't get to assume anything else. Okay, well, so we have an A of type alpha, so we should be able to make, oh, this is a little tricky. We can get rid of, so if we have the left side of the exist statement, right, we can kind of specialize the exist statement with A, but that's not, instead of specializing, we're doing it in the goal. So instead of specialize, we use apply. So we're going to apply exist.intro with X. Oh, but we don't have X. We have A, right? Yeah, so this A up here, we need this A up here to prove this, right? Now we have to show that R implies P of A. So now we have to give R to R implies X, R implies P of X. R implies there exists X such that P of X. So now we have an exists X, P of X. We need P of A. Well, I'm lazy. Oh, it didn't work. Okay. R implies X. Why do I keep saying X? R implies there exists is a thing we can break down using R cases or whatever you want. I'm going to use our obtain, get an exists to get an X and a P of X. And I'm not going to put this on a separate line as we're doing this. And now we just need to, okay, can't we just say P of X applied to A? Ooh, this is, did I do something wrong here? Why do I have such a, I can't use P of X to prove P of A, obviously. I have to do a proof by contradiction, don't I? Or maybe I did the wrong, so can't I apply the R inside the goal? Shouldn't I be able to do this? Convert right hand side, intro X. That's an intro. Of course, exact doesn't work inside a convert tactic. You're right. No. So for arbitrary tactics, you have to use tactic with the big arrow. in convert mode. So right now we need to show that for all a, p of a implies p of x. Of course, the last one has to be the hardest. Wow. So we can't say, there's no way to say, like, given that there exists x such that p of x, there's no way to say this is that a is the x that satisfies that proposition, right? It's true for some particular x, but you don't get to know what that x is. Just that it's of type alpha and that there's at least one of them. So I think we have to do a proof by contradiction here, even though we have alpha. I mean, even though we have a. It just feels wrong to use a proof by contradiction if we have a already. Should be able to say p of a by like using r implies x or something. R implies there exists x. So let's look at where things go wrong. We start with r implies there exists x such that p of x. And then we say we have to prove there exists x such that r implies p of x. Yeah, so there exists x such that p of x doesn't say that p of x holds for a. So yeah, whatever, proof by contradiction time. I don't really care. Maybe you don't need to do it, but whatever. Do I want to do it here? So now, let's see if we can give, okay, now we're really close, right? We just need to show that, wait, this didn't work. Whoops. R. I don't get to do this. Oh, these error messages are always so confusing. Yeah, it has type prop, but is expected to have type R, type prop. So R is a proposition. We need a proof of R. How come we got to do it last time? It did exist out of lim to get that variable. So let's try that first. No, that's not what we did. Wait a minute. Now I'm confused. Oh, it exists.intro. Okay. Yeah, so we used exist.intro there. So shouldn't we be able to do that at rmx? We don't get to do this. Okay, I bet simple do it, but let's see. Okay, I don't like this. I don't like this at all. What's going on here? We get to assume R. Oh my gosh, I'm silly. Okay. Okay, now we get to assume R. Maybe now we do the by contradiction. I don't know. What am I doing wrong here? This is so confusing. It seems like so simple too, right? Like there exists x such that R implies p of x. Well, then R implies there exists x such that p of x. So if I think about how we did this with and, this is just, this is basically just like saying P and Q implies R is the same as P implies R, or sorry, P implies Q implies R. No, P implies Q and R. That's not true though. That's not true at all. Okay, so this is some slightly different. I have to conquer, right? I'm gonna cheat here and try to use simple. Just because I'm super stuck. Okay, what? So if you ever get stuck, like I do all the time, you can use simple, and usually it's after you do by contradiction, introduce a variable, introduce the negation of the goal, and simple. And then you can see that it's changed multiple hypotheses. We now have not R somehow, and we have alpha implies false. So clearly, wait, is that enough to, sure this is enough. Oh, okay, it is. Wow. Okay, so if that works, right, but you don't know why it works, you put a little question mark after the simple, control dot, and it gives you all the lemmas that it used. So it's using not exists to get the for all. Yep. Yeah, okay. Yeah, I think I know how to do this now. Okay, so by contradiction, not exists. Of course, say we have for all x. R implies not p of x because not exists, and I don't remember exactly. So not exists, yeah, puts the, it's the for all not p of x. I'm too lazy to think about that. So for all x, okay, so this is going to be by intro x, and then we say intro r. I remember how to do this now. Exact next does not exist, but we can make an exists with x and p of x. Oh, interesting. Okay. We don't actually want the R implies. Don't really care. Oh, we do, because next there does not exist needs R implies, right? Okay, fine. But in our lambda, doesn't matter. We don't need to assume it, because you can always, if you have the conclusion of a implication, you can always make an implication from that. So, okay, so now we have for all x, R implies not p of x. We need to show false. We have, we specialize this, please. No. We can specialize the for all we just made with A to get R implies not P of A. Specialize this with R. No, we don't have R yet. Then we can say not exists. A and FA. So, oh, okay. Okay. So what we want to do is we want to say it suffices to show there does not exist. It suffices to show this. Whatever. Too impatient. I'm just going to say we have it. We have there exists by exists A and f of A applied to R. This one's particularly hard. Let's start with what we know. We know that R implies and exists. Right, so we have R, not R, by obtaining the x and p of x from R implied there exists specialized to HR after assuming R. And then we can apply that to there does not exist x such that R implies p of x. Wow, okay. So now what? Well, can we say, okay, once again, I'm too stuck. Not exist, once again. Okay, the hint does not exist. What happened to our for all? We specialize the for all to R implies not P of A. Okay, class filled up by contradiction is clearly, I think, maybe the wrong choice here. Maybe we should be doing EM on R. Let's get either R or not R. In the first case, pretty easy. But what about in the second case? We have not R. That didn't help us at all. There exists x such that p of x. Well, then there exists x such that R implies p of x. Well, maybe here's where we use them by contradiction, right? Because we need a p of a. So we can assume, how come this doesn't work? We have, there does not exist x. What? Okay. What? Well, that works. What? Oh my gosh. Wow. Okay, what is this monstrosity? There exists A1, this A1. Okay, this is not R. R implies false. We need to show an exist statement of A, and R implies not. Oh, I'm so silly. Not R means R implies anything. Okay, right. Okay. I don't think we even need this. So silly. Rename this to H not R. Just throw this in here. And we're done. So did we even use FA? Oh my gosh, we didn't even use FA, did we? All right. Okay then. So just to recap, we assume our implication. We do a proof by contradiction. We say that there's not R because if you assume R, you get there exists x such that p of x, but you can show that's a contradiction with there does not exist x such that R implies p of x, because once you obtain the x and the p of x, you can construct a new exist statement, even though you don't have, I mean, you don't even need R here. At least in the new exist statement, you can arrive at a contradiction. Okay, well, that was really challenging. Probably noticed the sunlight completely going away while I worked on the last proof, but we're done. We made it.